All right, now that we've talked about some of the basics of waves, we're going to get into some properties that all waves have. And I collectively call these the shun words, but there are four properties that every wave is going to exhibit. They all end in tion, hence the shun words. So the first one we're going to talk about is superposition. And that is the ability of waves to add together and combine to either create a bigger wave, to cancel each other out, to create a more complex wave. In all cases, it's just creating a new wave. Two kinds of superposition that we have are constructive interference and destructive interference. Constructive interference is when the waves combine to produce a bigger wave. This occurs in this situation here, where their peaks or crests are aligned and their valleys or their troughs are also aligned. That's a technical word for it, crests and troughs. And when that happens, those two waves combine to produce a wave with a greater amplitude. Okay, and that would be an example of constructive interference. Destructive interference occurs when the opposite happens, when a crest aligns with a trough and vice versa. Those two waves then combine to cancel each other out or to just create a smaller wave. All right, so that's going to be destructive interference. We also have the option that the waves just create a more complex wave, and we'll talk a little bit more about that later. So that's superposition. The waves are adding together. In all these cases, they're obviously in the same medium. They're somehow able to interact, and we'll talk more about how that happens later. But for now, we just want to know what superposition is. So here we see an example of superposition occurring. All right, so we have these two waves, really just two pulses moving along a string. They come together, they combine briefly in the middle to create a bigger wave. So that would be an example of constructive interference here. But they combine to create a bigger wave, and then they pass through each other. Okay, and we see here down at the bottom examples of each. On the left-hand side, we see step-by-step constructive interference. These two wave peaks go towards each other, temporarily create this bigger wave as they overlap, and then pass on through. And then we see an example here of destructive interference because it's a crest and a trough. They combine. In this case, they don't completely cancel each other out. They just create a smaller wave and then pass on through past each other. The next property we have is diffraction. This is the ability of waves to spread out when going through an opening. And so we see here, these are all meant to be like viewed from above wave fronts. Almost imagine looking at ripples in a pool. Okay, the wave fronts come in, they go through this opening. And what we see is they don't just go straight through like this. We might expect that there would just be a small, narrow wavefront going through. Instead, what happens is that wave spreads out, okay, going through the opening. And it kind of looks like the Wi-Fi symbol here, but it spreads out. And that's diffraction, okay, the ability of a wave to spread out when going through an opening. We also have refraction. Okay, and this is the ability of a wave to bend or change direction when the medium changes. We know that when the medium changes, we talked about this before, that means the velocity of the wave changes. Okay, and so we see once again these wave fronts going through the water. We go from deep water to shallow water, and so we end up experiencing a change in velocity going from this medium to this medium, and ultimately that changes the direction of our wave. Okay, when they hit this boundary that divides the deep and the shallow water, what we see is the waves are going and they make a turn. They change the direction in which they are moving. Okay, and that's because the velocity changes. That ultimately leads to a change in direction. The next property that we have is reflection. It's the one that we're probably the most familiar with. We take advantage of this many days when we look at ourselves in the mirror. That's just one example. There's many examples of reflections, but what reflection is in general is the ability of a wave to bounce off of an object and change directions. Okay, so we have a wave coming in here. Here are our wave fronts. They hit this boundary. They bounce off and they change directions. The type of boundary determines exactly how the wave reflects, and we'll look at that on the next slide. As I mentioned before, the type of boundary affects exactly how this wave reflects. So we see here a wave pulse coming in on a string, and the string is fixed in this case to that boundary. Okay, so you can imagine a slinky or a rope tied to one location on the boundary. What ends up happening is that wave pulse hits and it flips upside down. Okay, so we started with the crest, and the reflected wave that goes in the opposite direction ends up being a trough. So that's what happens when we have a fixed end boundary. The wave reflects and goes back in the other direction, but it's flipped now. On the other hand, if our boundary is free to move, like we have here, so maybe there's a little ring attached to our boundary, and when the wave comes in, it can slide up and down. What we end up seeing is that when it reflects back exactly the way it came in. So we have a crest coming in, it hits the boundary, reflects, and we have a crest going back out. So that would be a free end, a free boundary. We're going to talk now a little bit about resonance and standing waves, which result from some of these wave properties that we've been talking about. And they're going to play a really, really important role when we start talking about musical instruments, which is kind of the last thing we're going to do here with our waves unit. So resonance occurs for any oscillating object when the object is driven with a frequency that's equal to their natural frequency. We have a lot of examples of this, okay? One is pushing someone on a swing, okay? You push them at steady intervals along with the oscillation of that swing, which is basically a pendulum, and that helps them to go higher. It increases their amplitude. We see this with ringing a bell, okay? The bell swings back and forth, and we want to ring it at that same rate that pendulum basically inside the bell is going at. Bouncing on a pogo stick's another one. If you think back to that as a kid, right? You want to jump whenever the pogo stick goes down, and so that's basically an example of a mass on a spring, and you want to bounce at that rate to increase how high you bounce. Okay, so those are all examples of resonance, when an oscillating object or a wave is being driven at its natural frequency. When we're talking about resonance with waves, okay, resonance ends up creating what we call standing waves, and we'll take a look at examples of that on the next slide. Standing waves are going to occur when waves are in a confined space. Okay, so maybe they're in a fixed part of a string. We could have a fixed end on our boundary. We could have a free end on our boundary. That's going to affect what the standing waves look like, whatever that boundary condition is. But as long as they're in a fixed space, we have an opportunity for standing waves to form. And what that looks like is those waves in that fixed space end up having this steady oscillating state. So we see that here with this first wave, it's just oscillating up and back. If we have a slightly greater frequency, a higher resonant frequency, because there are multiple resonant frequencies for any fixed space, we see that we oscillate like this, but it's still a steady state, and we have two higher ones here. Right? And so what you would see if you were watching this, because these are oscillating fairly slow, if they're oscillating quickly, it would look something like this diagram here. Okay, and you see this steady state. You would see this wave going back and forth very quickly, and you'd see these steady states arise, and they look like they're fixed in place, and we actually do have points that are fixed in place. And so we refer to these as standing waves. And it happens when we oscillate this rope, okay, or whatever it is, at the right frequency, at one of the resonant frequencies, and the waves just fit nicely into that space. It leads to these standing waves. Okay, so we can't do it at any given frequency. It has to be the proper frequency. But when we hit that frequency, we end up with these nice steady states of waves just oscillating back and forth. And so the reason why this works is actually a combination of reflection and superposition. So what we have is we create waves. Those waves travel down the string, okay, and reflect off of the end. All right, so that's the first thing that happens, is whatever is driving those waves travels down the medium. I'm saying string in this case, but it could be other things. Travels down the medium, reflects off the end, and starts traveling in the opposite direction. However, we're continuing to generate waves. So those reflected waves that go off the end, okay, now undergo superposition with new waves that are being generated. All right. If we do it at the right frequency, one of the resonant frequencies, what ends up happening is the new waves and the reflected waves experience constructive interference, and this leads to an increased amplitude. So let's take a look at a diagram of exactly what that looks like. So we see an example here of two waves undergoing standing waves. So what happens is we have our initial wave going in. That wave is going to reflect off of a boundary, and then there's going to be a wave coming back out in the opposite direction. Those two waves are going to undergo superposition, okay? And when they have their crests aligned, we're going to have constructive interference. When they have a crest and a trough aligned, it's just going to be flat, but it ultimately leads to this steady state that we see here. Okay, because they're vibrating at just the right frequency, okay, they match up at the right intervals, and we end up with this steady state wave that we see on the bottom. You may have noticed on the last slide, but it's pretty obvious here, that we have certain points where the wave doesn't really move at all. So like right in here, right about here, okay, right about here. Those points are fixed, okay? They never really move from that position. The wave oscillates around them, but they don't move at those points. We call those points nodes, the parts that don't move. We also have parts that experience the full range of motion going up and back, okay, the maximum possible amount. We refer to those points as antinodes.